Hey, Juju.
Hey Greg, good morning. Thank you for joining us. Hope you're having a good day so far.
Yeah, so far so good.
All right, awesome. Well, I think we have a good number of people from all over the world here. So why don't we go ahead and get started? Let me love to introduce you. Thank you for coming on today. Everyone, this is Greg Fallon. He is the CEO of Geminus AI, and he's going to be talking to us today about leading the change, how autonomous multi-agent systems are redefining energy and the heavy industry. So thank you so much. I'll let you get to it.
Great. Let me share my screen. Swap displays. So Juju, which display do you see?
I see your presentation mode. You're great. Good to go.
Great. All right, excellent. Welcome, everybody. Thanks so much for joining. My name is Greg Fallon. I am sitting here in Boston. And today we're going to talk a little bit about what we've been calling the next industrial revolution, really how AI is impacting industry. And we're going to dig in a little bit to some of the peculiarities about deploying artificial intelligence in industrial settings and talk about some of the approaches that we've been using, which combine agentic systems along with highly specialized scientific machine learning. So let me dig in a little bit. First of all, just to give you some background on me, I came out of the engineering realm. So I left my PhD program in the mid 90s to join a startup at the time. And my specialty was really high accuracy simulations, specifically around engineering applications. So things like predicting external aerodynamics around airplanes or combustion in power plants, those types of things. So we grew that company. That became a publicly traded company called Ansys. And ever since then, I've been in and around this concept of engineering simulation. But about 15 years ago, as sophisticated machine learning techniques started to show up more prominently, I got really interested in the idea of combining machine learning with advanced simulations to really drive artificial intelligence in the industrial world. And so my co-founder and I started Geminus. My co-founder was a professor at Stanford. Now he's at the University of Michigan. He still maintains a role as our chief scientist. And what Geminus is, it's a company that sits at the intersection of what I would call scientific machine learning. And we deal with highly specialized machine learning algorithms that are very tailored towards engineering applications, high precision applications. And the thing that we think about all the time is how do you imbue machine learning algorithms and artificial intelligence with physics to give them context? And then how do we combine these machine learning algorithms together in such a way that they can really reason and inform the end user, who is typically an engineer or an operator. And you'll see that we're combining these techniques with advanced simulations, advanced mathematical optimization, and bringing them all together with an agentic architecture. So just to take a step back, I know some of you may be from the industrial environment, some of you may not, but I wanted to give you all some context about what it's like to be someone who's responsible for operating a plant or an oil rig or some large industrial system. So, you can picture yourself in the control room. You're in a massive industrial plant. It could be a gas pipeline. It could be a power plant, maybe a steel plant, chemical refinery, really anything. We can even take this down to airplanes or spacecraft. But when it comes to the large plants, every minute you've got huge quantities of materials flowing through your system, right? So think of an oil refinery. Maybe you're refining bio-based fuels. And you have, at any given moment, mass amounts of fuel, tens of thousands of liters running through this refinery at any given second. There's huge amounts of energy that are going into modifying these particular materials. So you're bringing together materials that are flammable with a lot of energy. The system itself is hugely dynamic. It's impacted by small changes in outside temperature, minute changes in the feedstock, humidity, vibration. There's a huge number of factors that are affecting how that plant is operating at any given moment. And to keep the plant running, let alone keeping it running at peak capacity, requires constant control adjustments. The decisions that need to be made that are sometimes done by advanced control systems, but most often with some sort of human dictating the operation of the systems. And believe it or not, in most industrial plants, these decisions are made by someone who's really working off of their experience and knowledge. And we're going to talk about that in just a second. But every decision that this person or control system makes is affecting safety, right? We're talking about plants that have a huge amount of energy and flammable materials. We're talking about the efficiency of the plant, right? If you've got massive amounts of material flowing through this plant, just small changes, a percent or a fraction of a percent, could mean millions of dollars a day. And then, of course, you've got sustainability, right? So these plants consume a tremendous amount of energy. In many cases, they're refining carbon-based materials, and wasting those materials have a huge impact on sustainability. And these plants often emit things to the atmosphere that are often carbon-based as well. So you've got a lot of this going on in the background. Now, if you take a look at this curve that I've got here, I just wanted to talk a little bit about some of the technologies that are used in these particular plants, right? It's not like we haven't applied IT technology to these plants. It started with IoT and analytics to give insights, but the problem is there's little context there. And often, sensors drift or aren't in the right place. And, the right place may change constantly because the plant itself is changing constantly. So analytics were a big win for the industry, but they were not the end all and be all. And then we move on to something which is my background and something near and dear to me, which is this concept of simulations. The engineers who are responsible for operating these plants will typically have pretty sophisticated physics-based simulation tools that are available to them. These tools are great because they can give you insight into what's happening at the plant under given conditions. You can get a whole range of really rich information out of these simulators, but there's some challenges. These simulators typically require an expert operator. Often it's a PhD. They require specialized software, highly specialized compute, lots of it. And the big kicker is that these simulations can take a long time to inference or to give you an answer, right? In some cases, we're talking days. And so the idea of using these simulators to inform decisions as they're being made is non sequitur. There are some simple situations where this works out okay, but in most industrial situations where it's even modestly complex, the idea of using the simulation in real time falls apart. A lot of times people will ask me, well, what about quantum computing? And that will make simulations faster. That'll be wonderful. But it's really hard to sit a quantum computer next to an oil refinery. So you still run into these same issues. And you can see I put a little blue dot here at the far right hand of my plot, where we're talking about a takeoff in performance efficiency of the plants and the information that's available to operators to make informed decisions. So let's dive in a little bit deeper and talk about the uniqueness of the industrial compute and data environments. And we'll talk a little bit about their fit for artificial intelligence, or maybe it's artificial intelligence's fit to solve the problems that operators of these plants deal with every day. So first of all, there's no denying that artificial intelligence does amazing things. This is a very silly image that I provided, but here you've got this incredible complexity of images being generated from text, and these images have an incredible disconnect from each other, and the AI is able to bring them together. So this is all good and wonderful, and it's incredibly helpful. But the problem is that even with the sophistication of the AI algorithms, the problem with the industrial sector is this last mile of this infinitely complex, dynamic uncertainty that's presented in these industrial plants. We think about kind of what's there. Let's dive in a little bit again and talk about an oil rig and what's happening on an oil rig, right? So again, you're in a high risk, high precision world. Let's say this oil rig is sitting in the Gulf of whatever you want to name it. I'm not sure what the name of our Gulfs are these days, but so it's many miles offshore. You've got harsh conditions, high winds, corrosive salt water. You've got shifting currents. You've got fantastic pressure swings from the wells that this rig is connected to, right? You've got gas coming up and bubbling from the wells themselves, mixed in with oil. And it's just a hugely dynamic environment. On top of all this, the equipment is changing minute by minute, right? It's getting older. It may need repair. It may go out of function. And complicating all this is the risk profile of the operating decisions that are being made, right? I mean, a single miscalculation can lead to catastrophic loss. So we know what happened in the Gulf of Mexico many years ago when the BP rig encountered a gas bubble coming from underneath. It was a catastrophic failure. It was an environmental disaster that we're still reaping the impact from. From an IT perspective, if you think about this oil rig, you've got data coming from a whole host of devices, right? I mean, there's sensors, not everywhere, but there are a lot of sensors on this plant, this rig. It's generating a huge amount of data, right? So some of the statistics out there, a single oil well can generate 9 gigabits of data a day, right? And think about how much some of the early ChatGPT models were trained on. We're talking about 25, 40 terabytes of data. Excuse me, an oil well generates about 9 terabytes of data a week. So in several weeks, you're generating as much data as was used to train ChatGPT, right? So you've got this massive amount of data, but it's not always in the right place. It may not be good data. And then on top of the data creation, there's really no high-speed network associated, at least with this oil rig, right? So you've got to connect to satellite. You've got latency issues. You've got bandwidth limitations. And then if you think about the computational power available on this rig, you're talking mostly about edge compute. And we're not talking about massive edge compute. Yes, you could put some pretty significant servers on this particular rig, but it's nothing compared to what we're used to having available to us from an AI perspective. So, what do we do to overcome these challenges, right? We've got a high risk environment. You've got a demand for high precision in a dynamic environment that's changing constantly with a huge level of uncertainty. So first is you've got to take a different approach, right? And I talked about the value of these physics-based simulators and the rich data that they give off. That's ideal because that data is fully in context. These simulators have been out for almost 30 years, 40 years now. They're highly respected. They're validated, and that's wonderful. But as I mentioned earlier, they don't work in real time. So as we take a step back and think about different ways that we can bring real-time intelligence to these types of these plants, we think about combining things together, right? So can we take a multiple intelligence approach, right? So can we combine machine learning models, right? Well, we think about typical machine learning models trained off of data. Those aren't necessarily good enough for this environment because they lack context, and any sort of hallucination can be catastrophic, right? So these machine learning models have to be trained in a very precise way with context. They need to have uncertainty bounds associated with them. And so there's a whole academic field associated to scientific machine learning, specifically physics-based scientific machine learning, which is my co-founder's background, that apply, right? So we can make use of those particular models, but then we need to apply reasoning, right? How do we apply reasoning to this? And we can think about mathematical optimization. That's fantastic because we can make recommendations based off of the data, but there's more to it. And that's where the power of LLMs and agentic models can come into play and be very, very helpful. But then there's another problem too, right? I mentioned earlier that these environments are dynamic. So you've got these machine learning models. They need to be very accurate. You may need more than one of them. Sometimes several of them loop together. So they have to be timed as they're communicating to each other. But they need to be up to date, right? So these industrial machines change constantly, right? And it's not just that the feedstock is changing, the machines age, so that model health becomes a major issue. So not only do you have to have highly precise models that can be trusted, they need to be able to be updated on a regular basis. And so this is where some of the advanced scientific ML techniques come into play, and we've built some of those into our platform. And so we have the ability to train models in an extremely short period of time on relatively sparse data. And these models can be extremely accurate. They have uncertainty bounds, a lot of the characteristics that are needed to drive decision making in this industry. So I'm going to speed up a little bit here. We're 15 minutes in, and I want to make sure we have time for questions. But I'm going to walk you quickly through a case study. This is a case study that we finished up last year. This is a commercial application dealing with an energy network. It's a network of natural gas wells that are connected together by pipes and compressors that take the gas and deliver it to a facility that removes pollutants from the natural gas so it's appropriate to sell. And there's a bunch of issues with these particular networks. You've got pressure changing constantly. As it comes out of the wells, you've got environmental factors addressing or affecting the pressure as well. And you can't have an overpressure in these pipes because you have a highly flammable gas, and an overpressure can lead to an explosion or a catastrophic event. So typically what will end up happening is the operator has to flare the gas, meaning release it to the atmosphere and try to burn it if there's an overpressure. And that, as all of you know, releases greenhouse gases, and they're the worst kind of greenhouse gases because there's a high content of methane in there, which traps a lot more heat than carbon dioxide. And so there's a really significant environmental issue here. And then, of course, for the operator, there's lost profits because you're actually burning the products that you're supposed to be selling. And so in this particular case, we took our approach, which is combining these scientific machine learning models, connecting them together, connecting them with advanced optimization and reasoning capabilities to deliver an application. We took about a month and a half to build this particular application, so it was astonishingly fast compared to industry standards, which are often 12 or 24 months on these types of applications. And the results of this particular application were astounding, right? So the application is equipped to an operator who can query the application. The changes in the network are updated dynamically in the application. And we found that in most cases, this intelligence would give the operator recommendations that in most cases eliminated the need to flare. It dramatically reduced the amount of energy necessary to move the gases to their processing facilities, and it overall increased profits, right? So this is the magic application that massively reduces environmental impact of this industrial process while increasing profitability for the owner of the network and the owner of the wells. Okay, so just very quickly, I'm going to kind of jump through these slides, but what does the next revolution mean?
So sorry to interrupt.
Yep.
20 seconds left.
Go ahead.
We have about 20 seconds left before this drops. So I just wanted to give you a huge thank you for coming on stage today and walking us through this, and thank you to the audience for listening. Appreciate it.
All right, thanks a lot, Juju. Thanks so much, everyone.
Bye bye.